Students, welcome to the tutorial number 3. Finally, today we will start with real, I would say, stochastic optimization. Maybe the topic which we'll look at today is the most important in all this course. It will be the mathematical stochastic optimization two-stage model, quite important concept. And our tutorial today consists of basically two big exercises. Or first one, it's not that big. It's some topic related to the mathematical optimization about the notation, about the matrix notation. And then in exercise 2, we will really start with the main part. It's the Dakota model. And on the example of this optimization model, we will check the stochastic optimization and two-stage model. So let's start then with the exercise 1. As always, I will turn off the webcam so we have more space. And this question is related to the materials from the lecture 1. So there you have slide number 47. Maybe slides updated, so it will be another slide number. And here you have the slide name linear problems in matrix notation. So before, on the first tutorial, we looked at the simple notation for linear optimization models. Then we looked at the sum notation of the models. And now we want to have a look at the one more notation. It's matrix notation. It's called matrix notation because the objects of the model will be represented as matrices and vectors. You can see here the example. So instead of writing some exact numbers or instead of writing this sums as in sum notation, here we'll represent the model using the cost vector, decision variables vector x. Right hand side here is only the vector b. Then we have the coefficients of the constraints a multiplied. A is the matrix multiplied by x, which are vector of decision variables. So what you see here, it's called the standard form. What is standard form? Standard form is the notation of linear optimization problems, as you see here. And the idea is that any linear optimization model, it can be transformed or it can be described using this notation. So any of the optimization model, it can be depicted as a model in matrix notation in standard form. And the only question that is, what are the coefficients in A, matrix A, in vector B, and in vector C? And what is the vector of decision variables? So what exactly it means, we will now look on the example. And the example is the exercise 1. So here we are given the more or less normal optimization model, linear optimization model, and we are asked to transform it to the matrix notation and to define which values or elements have vectors or matrices, so vectors x, c, b, and matrix A. So if I start solving this exercise, first of all, how this problem will look in matrix notation in standard form. We saw it before on the slide. So any model, and including this one, it can be represented in the standard form matrix notation. And standard form looks as follows. It looks as maximize Cx, then subject to matrix A multiplied by x less or equal to b, and x more or equal to 0. So x is positive. And what I wrote here, it's exactly what you have in the slide of lecture 1. Now, so what are the elements of all these vectors? Let's start from the objective function. So we see that in the standard form, objective function is maximization. In our problem, our objective function, it's minimization. So we need first somehow to transform this minimization objective function to maximization one. And the easiest way to do it, and quite intuitive one, it's to multiply all coefficients near x's with -1. So we can transform, or we can say that minimization of 30, oh, yes, x1 minus x2 is equivalent to the maximization of minus 30 x1 plus x2. Now, so we transform it from minimization to maximization. Now we're closer to the standard model. But the question is, so where are this vector c and vector x? And vector x, it is the vector of decision variables. What is the vector? I hope you know from linear algebra. It's just a column of values. So we can write down then vector x, x1 and x2. What is vector c? Vector c is the, again, vector of the coefficients near x. So vector c, it's equal to, what are the coefficients near variables x? For the maximization version of this objective function, it's minus 30 near x1, and it's nothing here, but we know that it's 1 near x2. And then according to the rules how we multiply two vectors, if we multiply c by x, it will be cx, and when as a result of multiplication, it will be exactly what we have here. So instead of writing all these numbers, we can just say that it's vector c multiplied by vector x, and then somewhere we can specify what exact elements vector x and vector c include or consist of. Now let's go to the right hand side. So or vector b. We see here that some matrix A. I know that it's matrix because normally in mathematics it has the capital notation, capital letter, multiplied by x. And we know already actually what is x. These are decision variables, vector of decision variables, is less or equal to b. So first of all, we see here that it's always less or equal. If I look at my constraints, which I have in the problem, and it is constraints are here, I see that I have an equal constraint, so it's equality, and I have one constraint which is more or equal on the line 2. So first step, it's like with minimization and maximization, it's to transform all the constraints in the problem, in this notations that we initially have, to the lesser or equal constraints. So first constraint, I don't need to change there anything. It's already less or equal. Now, this second constraint, to change the sign, so to say, from more equal to less or equal, I guess from the school you know that to do it, you just need to multiply left side and right hand side of the constraint with -1. So I multiply all the coefficients with -1 in this constraint, and then I can change the sign. So I write it down as minus x1 minus 2x2 less or equal, I change the sign, -6. Now, next constraint, it's not inequality, it's equality. What should we do here? The trick here is to represent this one equality with two inequalities. So I can rewrite this. I will write it here. So it's x1 plus 2x2 equals to 100. It's equivalent to, I can write it down as it's equivalent to basically two constraints. X1 plus 2x2 less or equal than 100, and x1 plus 2x2 more or equal than 100. And you should remember that between constraints in the optimization model, we always have and. So it's all the constraints should be true. And this thing works because if something is more or equal than 100, and if something at the same time is, if something is less or equal than 100, and if something is more than equal than 100, that definitely this something is always equal to 100. And that's what we say here, that if left-hand side is equal to 100, means that this left-hand side is at the same time less or equal and more and equal than 100. So we have now this. And now we see again, we need to have all the constraints that they have less or equal. And after this transformation of equality, we get one more equal constraint. So in the same way, we translate it to less or equal by just multiplying all its parts, all its coefficients by -1. So here is -1. Here will be also -1, and then less or equal -100. And the last constraint, it's okay. It's actually bound, but we can treat it as constraint. So it says that x2 less than 2. So we transformed all the constraints to less or equal. And now, what is the vector b here? Vector b here, it's the right-hand side. So it's this. So I can quite easily write down that vector b in this problem is 24 minus 6, 100 minus 100, 2. Now, what is, we found the vector b. Now, what is vector x? Yes, vector x we discussed before, it's the decision variables. And we see that here in the left-hand side, everywhere we have x1 and x2. Now, what is matrix A? And what's its elements? So matrix A here, these are all coefficients or elements of matrix A. These are coefficients of left-hand side. So it's 6, 4, here we have 1 or -1, -2, 1, 2, -1, -2. Here we have only x2, so we can write it down as 0x1, right? Plus 1x2. We just omit writing this all because it's assumed by default. So what again is the matrix A? From mathematical point of view, matrix is the table of elements, or it's several vectors. And in our case, for this problem, matrix A, it consists of all these elements which I underlined. So it's 6, first row, it's 6, 4, then it's -1, -2, then it's here, it's basically 1, so it's 1, 2, -1, -2, 0, and 1. And this is the matrix A. You see that the number of columns in this matrix corresponds to the number of decision variables. So it's x. We could imagine that the first column, these are coefficients of x1, second column, these are coefficients of x2. And the number of rows in this matrix corresponds to the number of constraints in the problem. And then if you multiply A, which consists of these elements, with vector x, so with this vector, as a result, you exactly get, as a result of multiplication of matrix with the vector, you will get everything what we have on the left-hand side. So this part. And the last element, it's x more than 0, but here we have already defined which is x. This is the vector of decision variables. And here on the right-hand side, instead of the vector b, we have scalar 0, which means that every element, so every decision variable here is positive. Now, so this was the, first of all, the matrix notation. And then it was the matrix notation standard form, which means that we take the problem and transform exactly in this standard form, which you found in the lecture and which we have here. One important thing is what would change if we would have, for example, here variable, one additional variable, and this would be not variable x, but it would be variable like y. So plus variable y, and then we would have something in the constraint. In the first constraint, it would be plus 1y. How would our matrix and vectors change? So first of all, this variable y, even so it has a different letter from variables x, still this vector is the vector of decision variables, whatever these decision variables are, whatever, in whichever way we define them. So if they have x or the letter y or any other. So if I would add here one more variable, I would just add one more element to the vector x of decision variables, and say, let's say that this variable is also positive. Then how would change my vector c? I see that this variable y, it has coefficient 1, so I would just add here one more element. Again, in the matrix, what would change? Since we have one more decision variable, we would add one more column, y, and this column, according to my changes, it would have value 1 only in first row. You can see here, because this variable y, it appears with the coefficient 1 only in the first row. In all other rows, it has value 0 in all other constraints. So I can freely put here everywhere zeros. And that's how what would change if we add one more variable. If we would add one more constraint, it's clear that we would just update the matrix A, how it looks. And this was the exercise about exercise 1 from the tutorial about the matrix notation of the linear problems. Next exercise about the Dakota model. We will first start to solve it and to model it without taking account of some stochastic parameters, and then we will start to include the stochasticity in the model. So without the stochastic parameters, it's quite a standard production model. So you can read through it to understand it, maybe stop the video. And so to sum up, we are the Dakota Furniture Company, and we produce 3 products: desks, tables, and chairs. And every product has some price, selling price when we sell it. Then, of course, to manufacture these products, we require the materials or resources. The resources are lumber, finishing, and carpentry, which is the labor of carpenters. Then it says here in the description that all the data is provided in the table. So we see that every resource, look at the second column, it has some cost. So lumber, for example, 1 meter of lumber costs €2, and carpentry 5.2. Then for every product, we have the requirement per one item of the product. So for example, desk, it requires 8 meters of lumber, 4 hours of finishing, and 2 hours of carpentry. And analogically, you can look at the table requirements and chair requirements of every material. Then also we have a demand for every product. So it starts at 115 for the table, and for the chair, it's the maximum demand among 3 products, it's 290. And then, of course, the selling price. So, and the question is, how can we maximize the profit? So again, the profit maximization problem, the same as it was on the first tutorial. We have strategically, we produce 3 products and have 3 limited resources. Now we are asked to formulate this model as linear problem. And we start its formulation from the definition of decision variables and objective function. But actually here we have already a tip. It says that use xi as the decision variable for the quantity of resources that we purchase, and yj for the amount of products that we manufacture. These are 2 things basically that about which we want to make a decision. And profit is the, so we want to maximize the profit. And profit is calculated as the difference. So profit is equals to the difference between sales and costs. Let's think, what are sales? So our sales, we have 3 products. These are sales of these 3 products, which we produce and sell. There is, again, nothing is mentioned about warehouse that we can store products. So basically, everything what we produce, we assume that we sell it, or we must sell it. So how are sales calculated? Sales, it is the production amount of every product. So it's Y1 for product 1 for the desk multiplied by selling price of the desk, which is 60, plus the same selling price of table multiplied by the amount of table that we produce, and plus the amount of chairs. The selling price of chairs multiplied by the amount of chairs that we produce. And of course, minus costs. So since we know what it is now, how do we calculate costs? Here we have costs are basically costs. These are costs of goods produced. So it's the cost of all the materials that we use for the production. And we have here the decision variable, x, which the meaning of which is it is the purchase quantity of resource. So of resource 1, 2, and 3, which are lumber, finishing, and carpentry. So let's calculate it in this way that our cost, this is basically sales minus, so profits is a sales minus cost, and cost consists of amount of lumber that we purchase, and every meter of lumber costs 2. So it's price of lumber 2 multiplied with the x1. 1, it is the index of lumber. Then minus price of finishing 1 hour, x2, and minus price of carpentry 5.2. So here should be 2, x3. And this is basically the objective function, so I don't need this anymore. I only need this, and due to the reason that we will see later, I will write it down. I will start in the formula with costs. So first we will have here costs, and then plus sales. But of course, whether we put here in this formula first cost and then sales, or sales and then costs, it doesn't change the final value of the profit. This is the objective function. Now let's find the constraints. What is really constraining us? You can think about it for a moment. But we see that we have here the materials. So we have limited materials and demand. Demand means that we cannot sell more than the quantity that customers want to purchase. But let's start from the materials. We did the similar thing on the first tutorial. So we start with first material, which is lumber. So first constraint will be for the lumber material. And so what is the available amount of lumber? Basically, we decided. So we see here the decision variable x1. It is the number of resource 1, lumber, which we purchase. So what I want to specify in this constraint is that the usage of lumber for the production should be less or equal than x1, right? We cannot use more lumber than we purchase. Now the question is, how do we calculate the usage of lumber? And we see that for the product 1, for the desk, we use 8 amounts of lumber, 8 meters of lumber. Usage of lumber, it consists of 3 parts. Lumber, which we use for the production of desks, of tables, and of chairs. The lumber which we use for the desks, it's calculated as 8. multiplied by the production quantity of desks, which is y1, plus the amount used for tables, it's 6, multiplied by y2, and 1, or we could omit writing this 1, multiplied by the production amount of chairs, y3. In the same manner, we populate constraints for finishing and carpentry. So these constraints look similar, except some coefficients and or indices. So for finishing, the available amount it's x2. It's the amount which we purchased of finishing, and the usage it has the same decision variables, but the now coefficients of requirements of this material finishing for every product. So coefficients are 4, 2, 1.5, and variables 1y, y1, y2, and y3. The last constraint, as the last material constraint is for the last materials that we have. It's carpentry with index 3, and here we have usage for the first, second, and third product, which is calculated as this. So again, here is plus. Again, very similar constraint, different coefficients. And now, after we have the material constraints, another constraint that we have is the demand constraint, because we cannot produce more products than we can sell. So how does this demand constraints look like? We had similar constraints before. So basically we say that we cannot sell and therefore will not produce more than 160 desks, because that's demand for desks. In the same manner, for table, we cannot, or yes, it makes no sense to produce more than 115 tables and more than 290 chairs. So the production amount the of desks is y1, and it should be less than the demand, which is 160. Then the production amount of the second product should be less than 115, and of the third less than 290. These are basically all constraints. The last constraints which we need for the formality reasons basically is that all variables that we have, in particular its production quantities and purchase quantities for materials, they cannot be negative, because we cannot produce negative amount of something. So we can write down that x1, x2, x3, y1, y2, y3 are less, or sorry, are more, of course, more or equal to 0. So this is the formulation of this problem in mathematical way, linear formulation of this problem. To have the complete model formulation, of course, we need to specify what a letter notation means in our model. And here we have only two, say, letters which represent the decision variables. So we write where, and then x is the purchase amount, xi is the purchase amount of material I, and yj is the production amount of product J. And of course, we know that we have here 3 materials and 3 products. Now we can make this model, linear model, and represent it in more compact way. So we can use the sum notation, which we looked at on the first tutorial. So you can shortly think about it, how you can rewrite it down and make shorter using sum notation. And I will now provide you the equivalent formulation in sum notation. So let's write here sum notation. Now let's first look at the objective function. It's the maximization, so we can continue with maximization. But now, how can we rewrite the cost? So we want to rewrite these guys somehow. And if we look closer, what actually we do in the costs? We multiply every decision variable, which is representing the purchase amount of material, with the cost of this material. So what we actually do, we find the sum, and since here everywhere is minus, so it's the negative sum. So it's equivalent to the negative sum of Ci, which is the price of material I, multiplied by Xi, which we already defined here. It's the purchase amount of material I. And this whole thing can be rewritten in much shorter way. Now let's look in the same way at the sales. How can we rewrite the sales? And we see that in the sales, what we do, we basically find the sum of 3 elements, and every element is the multiplication of the sales price of some product, and we have 3 of these products. Therefore, I can write it down as the sum of the sales price of every product J multiplied by the production amount of this product J. So I can rewrite all these guys. Now, of course, there is something more missing. It's the sums. They should specify for which element, so which values this I and this J they can get. And for that, I will say that I, so find the sum for every I in the set, which belongs to the set K. And K is the set of materials, which includes 3 elements, 1, 2, and 3. And then in the same way, I can write down that J is the set of products. It should be in the set of products, which will be named Sn. Let's shortly write down these specific elements, which we now define. So I write down here where as an explanation. So what I will not again explain what is X and Y because we had it here, but I should specify that K, it is the set of materials, and N it is the set of products. Now, before on the first tutorial, we used a bit another approach in some notation. So we use something like that sum of some elements where, for example, J starts from 1 and ends with 3. And for our example, if set n it consists of elements 1, 2, and 3, which we have in our case. These two statements are actually equivalent. And statement for the material, it's also, we know that we have 3 materials. So it's 1, 2, 3. And in the same way, this statement which we have here, it would be equivalent to statement that I starts from 1 and it ends with 3. And these two are also equivalent. And here we have some elements. If we would have here like 4 materials, let's imagine that we have here also material number 4. Then in this sum notation where we use sets, we wouldn't need to change anything. But here in the sum notation where we use indexes, we would have to change their end element from 3 to 4. And then it would be equivalent. So it's like slightly different type of sum notations. Both of them can be used. So this was the objective function. Now let's look at the next constraints, which are material constraints. And in material constraints, what we actually do here, we see that basically for every material, and we have 3 materials, constraint is very similar. In the left-hand side, we multiply the coefficients which represent the usage of every material to produce every product. We multiply with the quantities produced for every product. And here we have 3 products. So this index of y, it changes from 1 to 3. And on the right-hand side, we have x and then index of the product or of the material. So we can write it down for the first material as the sum. We'll look at the exact indices in the sum later. Then of the coefficient, we will call this coefficient W. So this is the usage of resource. Then the usage of first resource, it will be first index of W, because we talk here about the first resource. And then we see that we have different indices because every column here, so to say, is related to different product. So the second index is J, which is the product. So together this coefficient means that it is the usage of material 1 to produce product J. We multiply it with the production amount of product J. Then in the left-hand side, how this J changes? It changes from the first product to the last product with index 3, but we can again use here indices. So J, it belongs to the set products, which is in our case we named n. And this is the left hand side. And then right hand side, that of course this should be smaller than x of resource 1, because we now talk about the first resource. If we now look to the second resource, which is actually finishing, nothing will change except that this index, first index of W, which represents the resource, it will be instead of 1, it will be 2. And then x also, it will be not purchased amount of first resource, but of the second. So we will change it to 2. And again, if we will look at the constraint for the third resource, the only what we will need to change, it's again, it will be only these 2 coefficients. It will be 3. So now if we want to really have the abstract model in some notation, we can substitute this coefficient related to the resource with letter I. And we say that for this constraint should be like that for every resource. And so for every resource, we can say that for every I in the set of our materials. And set of materials, it's K. These are the material constraints. I will move it below where we prepare the model in some notation. So this is, and here we see that in addition to the decision variables which we defined before, we also added here the coefficient W. So we need to explain in this where statement the meaning of this coefficient. So the coefficient Yij, it is the consumption of material I like this, to produce, so to produce one item of product J. And of course it has 2 indices because it, so to say, connects 2 entities, every material with every product. And the next constraint that we have, it's demand constraints. We see that on the left-hand side is the production amount of product 1, 2, and 3. This is the variable Y. And on the right-hand side is the demand of this product. So it's quite easy. On the left-hand side, we have Yj always. On the right-hand side, it should be lower than the demand of that product. So it's Dj. Yes, so I will copy it. And here we have new coefficient or parameter. It's Dj, and it is the demand of product J. Of course, the last constraints that we have are non-negativity constraints, so we can write them down as the last line. So it's and it just states that X and Y are more than 0. We don't need to write down the exact indices. And this was the linear problem, exact problem reformulation using the sum notation. Here we shouldn't forget that it's for every J in the set of products N, of course. Yes, and it was the basically solution for the exercise 2, bullet point A. Now we are asked to, in the exercise B, to assume that the demand is stochastic. What does it mean stochastic? Stochastic means that We don't know it for sure. We can only assume it, the demand in this case, with some probability. And you see here we are provided the table, and it says that there are three scenarios or three possible options for the demand, what it can be in the future. Scenarios 1 to 3. Every scenario has some probability from 30 to 40%. Of course, the total sum of probabilities is 100%, which means that one of these scenarios should definitely realize or happen to be true in the future. And then this part of the right part of the table, it specifically provides the possible demand in every scenario for every product. So for example, in scenario, according to scenario 1, which has the probability of 30%, the desk will have a demand 50, table 20, and chair 200. In scenario 2, demand for every product will be a bit higher, or not even a bit higher, but sometimes many times higher. And in scenario 3, which has probability 30%, this demand will be even higher. So basically, this table, it provides us some data which makes demand which we have in initial optimization problem to be stochastic. And demand it's a parameter, so such parameters we call stochastic parameters. And this scenario, this case, it's quite probable in the real life, because who can know demand for the furniture products or any kind of product in the future to 100%? We can only assume it. Now, when you have this model formulation, so we can think here about several questions, and these questions, they are listed here. So first of all, we are asked to say what is the optimal purchasing and production quantity for every scenario. So here we are asked first to look at this scenario separately. Yes, and it's scenario 1, 2, and 3. And then say what would be the best decision if scenario 1 realizes, or scenario 3, or scenario 2. Before we answer this question, we will shortly look at the notation which you have in the lecture, and maybe it's a little bit cryptic, so we will apply this notation to the problem. First of all, we are given here the omega, which is the in the set of capital omega, and this capital omega is just the set of all the scenarios that we have. In this problem, we have three scenarios. So capital omega, it's the set of scenario 1, 2, and 3. Yes, and then this omega should be one of these scenarios 1, 2, and 3. Then psi omega, it's all the stochastic data of the scenario omega. What does it mean? So psi omega is the index of some scenarios in scenarios 1, 2, and 3. So this is the vector of stochastic data. In our problem, in this example, stochastic data, it's only the demand. Only demand is stochastic here. So we have now the demand for product J, so for the first product, and then for scenario omega. For example, first, the demand for the first product for scenario 2, it's first product, it's desk, scenario 2, 150, right? So for omega 2, this is equal to 150 for the first product. Then we have the demand of product 2 for some omega scenario, and demand of product 3. This is the set of stochastic data. Theoretically, it could be that we would have, let's say, stochastic consumption of materials, of material I for product J. We would have it different in different scenarios. So this vector, it could include some other values, elements. Then it states here that Z it's the value of objective function. This that it has two parameters, x and psi omega. So what does it mean? It's the objective value of the problem for the scenario omega when as decision variables x, we use some x decision variables. So I will write it down. So z is the objective value or value of objective function for some x. These are decision variables, this x of any what which we take. That's why it's a parameter for the scenario omega, and it means that for the case when we use the data, which is in our example demand of scenario omega, and I will write it down here. So it's optimal value of optimal value of not optimal but objective function for scenario omega with x decision variables. Now we have here x dash, and x dash you see again for some psi omega, or for some scenario omega, it is the optimal value of decision variables x, right? So x dash. So here x, it's any values of decision variables x. X dash, it is the optimal values. So the values of x that provide the optimal solution, optimal for a scenario omega, or for when we use data psi omega, so data from the scenario omega. And of course, now if we take this optimal value of these decision variables and put them inside the objective function, then this objective function with the decision variables that have optimal value will be the optimal value of objective function. So it means that if we put that, and here instead of some x, we use this optimal x dash for scenario omega, and we use data of scenario omega, then it will be the optimal value function for scenario omega. And you should see that in all these assumptions, we look only at the decision variables x, and there is some reason for that, because we everywhere assume that decision variables y, they already have the optimal value. It means that in this exercise, when we are asked to find the optimal solution for every scenario separately, for scenario 1, 2, and 3, what we need to do, we need to basically find this x dash, and then we are asked to calculate the optimal value. So what will be the objective function for this scenario with this x dash for that scenario? Now, you will find in the solutions this model in Excel solver. So this is the formulation of the initial model in the Excel, right? We have here decision variables, which are x and y, purchased quantity and manufactured and sold quantity. we have parameter demand, we have other parameters, then we have, as always, constraints, and some objective function with objective value. Now you see here that we have the demand from the deterministic model. So it's the initial model that we have. You see 160, 115, 209. And it's exactly the same here. Now, if I go to the solver and solve it, I will find the solution for this initial deterministic model, which is not that interesting for us. Now, how this model will look for the scenario 1? Because now we are asked to find the optimal solution for every scenario. Basically, the only thing that we need to change is the demand, because demand is only different between the models of every scenario and between the deterministic model and the stochastic model for, or let's say, model of scenario 1. That's the only difference. So we just have here the demand of scenario 1, and if we put this demand in our model, this will be the optimization model for the first scenario. Now, I can solve it. So basically, I find out the answer to the question, what should be my values of decision variables, if I assume that scenario 1 is coming with this demand. And if we go back to the notation, so when we solved this model, we found x dash for the scenario 1, or for the data, for the model with the data from scenario 1, psi 1, and it's basically the demand. And this solution or value of decision x decision variables is this. So it's equal. Now, what will be the value of objective function? So it's z basically with this solution x. I will write it down. So it's when we take not some x, but x dash. And it's equal to 1124. Okay, so it was the first scenario. Now we do the same thing for the next scenario. So for the second scenario, the only difference is also this demand. So I copy the demand. And then find the solution. So the x for scenario 2, x dash. This. And that when we use this optimal solution, it's equal to 3982. And I found the same for the third scenario. Now we see these are the values of objective function, optimal values. And of course, since demand is increasing from scenario to scenario, the highest demand we have is for scenario 3. Now, we did it, it's very nice, but the problem that we don't know which scenario in the future exactly will come, right? So we know that some of these scenarios will realize, one scenario out of three. So it's very nice that we evaluated every scenario separately, but we need to apply some techniques to make a decision and take into account three scenarios that we have. And there are basically three approaches how we can do it using the information about the scenarios. And first approach, it's in the exercise C. So we are asked to find the expected value solution, and then they calculate the expected value of expected value solution. So that's the first approach how we can evaluate or find the answer to this model which has stochastic data. And the idea is that, all right, we see that there are three scenarios, they have probabilities, and for every product, the demand is different among the scenarios. But why don't we just take some average value? So why don't we calculate average or expected value for the desk, for the table, for the chair, and then use these expected values as the demand in our model and find the optimal solution for that model, and this will be our decision strategy. So we can go back again to the notation in the lecture. Maybe it will be useful. And you see here that Z, so it's the expected value problem, which uses the expected, which provided the expected value solution. So this model, it's, you see it's the maximum, so it's the optimization model, or Z it's the objective function with some x and with psi dash. And psi dash is the not the data from some specific scenario, but you see here it's the expected expectation of this psi. So it's the expectation of all the data. Now, how does it look in our example on the in Excel? When we go back to the Excel, or yes, we see here it's already expected demand is calculated. So for every product, we calculate the expected demand. For example, expected demand for the desk, it's equal to 30% multiplied by 50 plus 40% multiplied by 150 plus 30% multiplied by 250. This is the expected demand for desk. This is for the table, and this is for the chair. So we can write down here expected value model, and we can write down that instead of psi omega, we use psi dash, and this psi dash, it's equal to 150 125 and 300, right? And then the x psi dash, so it's the optimal solution of x when we use this data. It would be equal to, we go back to Excel, instead of this values, we now copy the expected value demand of the expected demand, and we optimize it. So I just resolve it. Great, I found the solution. So the solution of x for this expected value model is like this. In the same way, I copy it here. And then what the value of objective function, it's 4165. So I can also use the notation which we had previously. So it's equal to 65. So we found the value of objective function, we found the solution, but actually, how can we evaluate the solution? If it's good or bad? And also, how can we use this solution? The problem is that basically, this data represented by psi dash or expected values of the demand, they will never happen because according to the problem description, the in the future one of these three scenarios will realize, but not some middle scenario. So we need somehow to evaluate the solutions that we found regarding these three scenarios. And before we do it, let's go shortly to the more to the terminology. So in the lecture slides, you have a description about the problems with recourse and without recourse. And we are interested in this two-stage approach with recourse. What we're here interested in is that we can divide all our decision process into several steps. So first step is that we make some decision, then random event comes, and then we can make a recourse decision. So it's something like we can modify what we decided in some way. How does it apply to our problem? So random event, sorry, it's the demand. So as for now, we are planning now for the future, and in some time, demand will realize, and it will be one of these three scenarios, but we don't know which exactly. And then we will be able to apply also some recourse decision. What is this decision described here? This decision, in our context, it's a decision about the quantity of material that we purchase. So these are the related to the decision variables xi. So as for now, we decide, all right, how many materials will we buy? Then some demand will come to reality. So we will start to get orders from our customers. We will already have the materials in our warehouse. And then we will make a decision of how many exactly products we produce. So this production related or manufacturing related to decision variable y, it's the recourse decision. And the x is the decision which we made now before the demand realizes. As for now, we cannot make the decision about manufacturing because, or we can, but we can't because we want to wait for the demand. We cannot postpone this decision process of how much of resources we purchase, because if we wait till the demand, it will be too late. That's how we can apply this logic to the problem and how we can interpret this problem. And also we can divide this problem into two stages according to the decisions. So first stage is this decision which we make now, which is related to the number of resources. And second stage is the decision which we make after the realization of the demand. And now, if we come back to what we did here. So this x, now it's not only the, in our interpretation, it's not only the amount of materials that we purchase, it's also the first stage decision. So x is the first stage decision here I have too much. Let's decision, and it's also the decision about the amount of materials and why for every scenario it's second stage decision. And a second stage decision we will make the amount of goods that we produce only after demand happens. So according to this expected value solution, we decided in the first stage decision that we will produce this amount of uh, not produce, but purchase this amount of materials. When we purchase this amount of materials in the future, when demand realizes, we will only then decide how much of the products will we produce. So what will be our now solution for the case when first scenario realizes? How can we calculate it? First of all, we will use the same notation. So it will be Z. Then in the future, when first scenario realizes, we have already made a decision about variables X. It will be this X psi dash. And then what will be the data in the first scenario? Of course, it will be the demand from the first scenario. Again, this, what we found here, we don't even basically need it because this demand, it will never happen. But this demand or this data psi1, it might happen, and we will already have the amount of materials that we decided now using this expected value approach. So what will be then our optimal solution? For that, we come back again to the optimization model. And as I say, in the future decision variable about the purchasing of the materials, it will be actually something what we cannot change. We already did the decision about it. So we need to basically fix these decision variables. So it will be something what we already have. The only what we will be able to make a decision about, it's about the purchasing of the, not purchasing, but of the production. And then the demand in the first scenario naturally will be the demand from first scenario. So we need to substitute this expected value demand with the demand of the first scenario. And that what says this psi1. So here we see that x dash psi dash is the optimal first stage decision variables. And the data demand is from the scenario 1. And let's see which demand will we have. Not demand, but solution. So we go to the, again, solver. Here, we need to modify the array of decision variables because now x is basically not a decision variable, it's a parameter, so we are not allowed to change it. And that's all that we need to change. We now solve it. And we see that we have not a profit, we have basically losses, minus 4,035. Let's think for a second, why do we have these losses? The reason is that in the first scenario, the demand, it's very low. And when we made the decision about how much of materials we purchased, we used here not the demand of the first scenario, but the expected demand, average one, which is much higher than this demand. The basically first scenario is the worst scenario. And it means that we purchased so much materials and they will be laying on our warehouse, and we will not be able to use them in case if first scenario comes true. So this is the objective value of the first scenario. Now, next, what we need to find out is the exactly solution with the same first stage decision variables, but for scenario 2. And to do that, we'll leave here everything as it is, because still we assume that we will have this amount of materials, but now we change the demand to the demand from the second scenario, and this demand is much higher. So I assume our losses will be less. I re-optimize the problem. And yes, now we have not losses, but profit. And let's do for the last scenario, scenario 3. Great. So we found these values, and now, so what do we do next? Let's revise what we did before. We assumed that the demand is the expected demand. Then we just substituted the demand which we had in the deterministic model with this expected demand, which is here. And then we found the solution for the first stage variables or variables about the decision how much of every material we purchase. So this is the decision that we make now. We purchase this amount of materials. And then here we calculate what will happen if we have this amount of material and the demand of first scenario realizes. And we modeled what will happen if the demand of second scenario realizes and the demand of third scenario realizes. So we got these three values. So now how can we unite these values? What is the probability that this happens? This first line related to scenario 1. This probability is equal to the probability of the first scenario. And the probability of the first scenario is 30. Yes. So the probability is 30%. What the probability that this one will happen if we use the variables x, which we found from the expected value solution? The probability is 40. And here again, it's 30. So what we can find when we know the probability at the outcome of every scenario, when we make decision using this first approach of expected value, it's quite easy. We just found the expected value. And this expected value, which we call EEV, meaning the expected value of expected value solution, it's equal to 0.3 multiplied by minus 45 plus 0.4 multiplied by this and plus 0.3 multiplied by, and it's equal to 1545. So again, this is our expected result, which we will get if we will make a decision about first stage based on the expected demand, so expected value of stochastic parameters. And that's what we were asked here in this exercise, and it's related to the first solution approach to the stochastic problems. If I go back to the lecture, we have here the formal definition of this approach. So again, here is the expected value of the problem. And then here you see it's the EEV, it's the expected value. That's why we needed the probability of the solution for every scenario. So for every psi omega, when we use first stage decision variables, which we found in the as a solution of the expected value problem. So that's what we did now. Now we go to the second approach. To the most important approach, it's stage stochastic model, and also it's called here and now solution. So it's here and now two-stage model, stochastic optimization model. And the idea is the following. All right, if we want to, so to say, we are interested to have this value outcome that we get as high as possible. So here it's 1545, but we are really interested to have it as much as possible. And here we make a decision about the first stage based on the expected value parameter. But then maybe it would be more useful for us if from the very beginning we build one model in which we maximize the expected profit. So in deterministic model, we maximize the profit. And here, since we have probability, we maximize the expected profit. So we'll now start building this two-stage model from the objective function, and then we will look at the constraints. So how objective function in this model will look like? We want to maximize expected profit. And the expected profit equals to probability of scenario 1 multiplied by the profit of this first scenario plus probability of scenario 2 multiplied with the profit, which we will get if scenario 2 happens, and plus probability of scenario 3, which will happen if profit 3 will happen. We want to maximize it. Now let's expand it more. How will the profit of scenario 1 look like? So I will write down probability of scenario 1, and here comes the profit for the scenario 1. Let's look at the objective value, objective function of the deterministic model. I will take this the most simple approach of the model. So I copy this. Move here. Let's now these are the first stage decision variables. This is a decision that we make now. regardless of the future. This is because we need now to make a decision about the uh, amount of materials we purchase. Because later, when we know the demand, it will be too late. So this is the first stage decision variables. But this part of the objective function, it's related to the manufactured quantity of the products. And as I said before, according to the specific of this problem and the approach that we use, we can decide how much of the product exactly we produce after demand realized. So since now we talk about the uh, first scenario, what we need to modify in this deterministic objective function to be the objective function of the first scenario, it's to add index to every second stage decision variable. And this index is the scenario number. So I added index 1 because this is the decision, these are the decision variables related to the scenario 1. And now they can be interpreted as the manufacturing amount for the product 1, for example, Y11, which, so for product 1, which will produce in scenario 1, for product 2, which will produce in scenario 1, for product 3, which will produce in scenario 3. And this all together here in the brackets is the profit of the first scenario. Now, as you might guess, we can now formulate the profit of the second scenario because we want to maximize the expected profit. So it will be the probability of the second scenario multiplied, and I can simply copy this all here. What I need to modify here is only the index of the scenario in the second stage decision variables because it's related to the second scenario. But in the second scenario, my costs of the purchasing material purchasing, they will be the same, right? Because I make this decision now, and this cost I will experience before scenario 2 realizes. So this cost, they are the same for all the scenarios. And now for the third scenario, of course, it's actually the same. Except this second stage decision variables, which are now related to scenario 3. And here we need plus. So that's the calculation of the expected profit, which we want to maximize. And now you can see here that you can do slight optimization or make this much shorter because since costs are the same for every scenario, and since the sum of the scenarios is always equal to 1, we don't need to include this cost in the clamps here. We can take them out of the clamps. So I can just move it out. And can just multiply this P1 and the costs, since they are related to the first stage and they don't change from the scenario to scenario, I don't need to multiply them. So it's like this. Then here the same. I have already here the costs. So here. Yes, so this all is now an expected profit of our problem, and we want to maximize it. This is the objective. Now we have the constraints. The assumption of the two-stage stochastic problem is that whatever scenario comes through, constraints should never be violated. It means in practice, or in this case, that we need to basically copy the constraints for every scenario that we have. We need to make a copy of constraints for that scenario. So let's go to the deterministic model. Here are the constraints of the deterministic model. I will copy them. And whatever scenario realizes, this constraint should be true. So from these deterministic constraints, I will now create the constraints for the scenario 1. Make constraints for the scenario 1. I just want to specify that when we look at the material constraints, that the consumption, so it's scenario 1, that the consumption of material 1 to produce product 1 in scenario 1, of product 2 in scenario 1, and product 3 in scenario 1, it should be less than x1, which is the amount of materials that we purchase. X1 doesn't need the coefficient because X1 is the same for every scenario. Only the decision about production quantity. It's different for every scenario. Then I do the same for the second material. So all the decision variables should have index 1. And here again, they also should have index 1. Now, when I go to the demand constraint here in the left-hand side should be the production of goods or of product 1 in the first scenario, of product 2 in the first scenario, product 3 in the first scenario, should be less or equal than the demand of that product. And the demand in the first scenario, it's not 160, 115, and 290. It's not here. It's 50, 20, 200. So it's 50, 20, 200. And of course, I will shortly write that x and y should be more than 0 as always. This was it for scenario 1. Then for scenario 2, if scenario 2 realizes, it should be basically almost the same. So for scenario 2, we'll have the same thing, except the coefficients, the indices are different. And of course, the stochastic parameters are different because in the second scenario, demand is different. So here we have everywhere scenario 2 index. And the demand is 150, 110, 225. Here should be plus. Of course, here we have also scenario 3. And again, it will be in the same way as in two previous scenarios. So the idea of the two-stage optimization model is that we optimize the expected objective function, so it's expected profit, and we calculate it as the part of the objective function with first stage decision variables. We don't change it, as here was x, I explained why, and then second stage variables for every scenario, they are multiplied with the probability, and when we sum up this part of the function for every scenario, we find the expected profit in this case, and then we make a specific set of constraints for every scenario. Now, and here we would write down then that so the parameters are almost exactly the same as the deterministic models. The only change that we have to specify here explicitly is that y j s is the production amount of product j, as it was in a deterministic model, in scenario S. Where, of course, so this is the two-stage stochastic optimization model, and we're, of course, asked to find the solution. So to find its solution, we just need to put all these constraints and this objective function into the software. And it's to put it in Excel solver, it's quite tricky. That's why in the future tutorials we will use special software. But I already have specified it in the solutions. So you can see the stochastic model. It's quite huge and it takes some time to put it. But here we have already the optimal solution. So first of all, our expected profit according to this strategy is 1,730. I will write it down. Let's somehow make it. According to the previous approach, when we just didn't do all these complicated things, but we just used the expected demand, our expected result was 1,545. So it was lower. Before we describe this result, let's shortly go back to the solution and see what we have here. So here we have the quantities of every material that we want to purchase, and it's the same for every scenario because we made this decision now. And here we have the so these are decision variables, the amount of products that we produce and solve. So for the first scenario, for the second scenario, and for the third scenario. And you can see that basically like the amounts which we will produce depending on which scenario realizes. But as for now, when we build and solve this model, we don't know which scenarios realizes. And now if we go back to the solutions that we get, so EV it was 1545. I will write down here again. And this is the expected result which we had when we were using very simple approach of this expected demand. Yes, expected value. Here and now solution, it's one which we get from the two-stage problem, and it's quite advanced technique. So we see that we get some extra, we win something when, or we win some expected profit when we apply this advanced technique. And this difference, which we calculate as 1,730 minus 1545, 45. It's equal to 185. It's called value of stochastic solution, VSS. So this is the value in our objective function, which we get when we apply this more advanced two-stage stochastic problem in comparison to expected value solution. So it's VSS. And now we have also the third approach. It's here, and actually here it was provided that if optimal solution of the two-stage stochastic model is 1730, what is the VSS? So you don't even need to build this big model in the solver according to exercise. But next E, you are asked to do it at home. So you have some information in the lecture and also in the tutorial solutions. You can have a look at it and maybe ask some questions if you don't know how to do it. And then we go to the exercise F. So here we're asked to find the wait and see solution. This is the third approach in addition to expected value and stochastic and here and now solution. We have wait and see solution approach. So wait and see. And what's the idea here? Basically, this approach is more theoretical. It's used to analyze all the solutions, and you can never apply it in reality. The reason why you cannot apply it in reality is this approach is the approach of someone who could see the future. So imagine that you have some manager, you know that this manager can see the future, what will come, which scenario will realize. So he knows exactly, will it be first scenario, second scenario, or third scenario? And therefore, you are asked, how do you expect what will be his profit? The thing is that you know that he can see the future, and he knows exactly what will be the future scenario, but you don't know what will be the future scenario, right? But still, you should somehow to define his expected profit. So let's start to evaluate the situation. If this superpower manager knows, if he knows that scenario one will be in the future, what will be his decision? What will be his value of objective function, his profit? Basically, we already answered this question. We answered this question when we calculated the optimal solution for every scenario. Because if he knows that scenario one comes in the future, he doesn't need to make any of these like expected value things. He just makes the decision of first scenario, which is now he will purchase 120, 240, and 130 materials because he knows that the data will be psi1, and then his profit will be 1124. The same if he knows that the second scenario will come to the reality, his profit will be 3982, and 3 it will be 7450. So we can just copy these values, which we calculated before. So it's like this. If scenario 2, he will make decision best for scenario 2. And if scenario 3, his decision will be like that. Decision, and this is the value of objective value. Now, you don't know which of these scenarios will realize. You only know which profit he will get. but we know the probability again of every scenario. It's 30, 40, and 30% respectively. So you, as someone who doesn't see the future, you can calculate his expected profit. And expected profit will be, so it's wait and see solution, which is his expected profit of this manager who can see the future. And it will be 0.3 multiplied by 24 plus 0.5 multiplied. And the answer is 41.65. So it's one more approach, which we cannot use, unfortunately, in reality because we cannot see the future. But how this approach is useful? You see that this manager who can see the future, he would get expected profit 41.65. And our outcome, if we use even stochastic model, it's 1,730. So let's calculate the difference, which is 41.65 minus 1,730. And this difference is equal to 2,435. So how is it called? It's called the expected value of perfect information. So perfect information, it's something like ability to see the future. And it shows us that if we would know the future, we would expect as this manager to get extra 2,435 euro of income. And how one can use it in reality. So for the case of this company, you could imagine that it would be quite a good motivation for them to lower this stochasticity. So to make their predictions have a high quality or to lower the dependence on the future demand. So they could, for example, find some better analysts or improve the analytics so that they have not three scenarios, but two scenarios. One does make sense, two scenarios, so that they have a less of stochasticity in their model. In the lecture, we have example with the farmer. So for him, it would make sense. He gets stochasticity from the weather. So for him, it would make sense to maybe use some chemical which lower his dependency on the weather in the future. So that's why you cannot use this approach in reality, but it helps you to analyze the problem. And now, after we have these three approaches and three solutions for them, let's write them down. So it was expected value of expected value solution. The easiest one when we don't know any kind of stochastic optimization and we just take the average demand, average stochastic parameter. Then we had here and now solution when we use the stochastic optimization and two-stage model, which is more complicated. And then we have this wait and see solution, which is not realistic for someone who can see the future. Now, if it's the maximization model, and if you didn't do any errors in your calculation, it should be always the truth that wait and see is the best solution. It gives you the highest number for the maximization problem. So the best means the highest number, and then it will be naturally be more or equal. It can be equal if the stochasticity plays no role. Then here and now solution, and here and now solution, when we apply a stochastic model, it will be always equal or better than the expected value of expected value solution. So if you have maximization problem, you build this two-stage model and you see that it has lower values than expected value of expected value solution, it should be something wrong. So it's like this for maximization problem. Naturally, for minimization problems, the best solution is one that has the lowest value. So these signs, they will be opposite for minimization problem. And so this was the bullet point F, where we found the wait and see solution, and we calculated the expected value of perfect information. And now we go to the, it's like maybe even fourth approach, scenario analysis. And it's more like an algorithm. So in your solutions, you have this algorithm, which is the screenshot from the lecture. And we can just go step by step through this algorithm. So first step is for every scenario I, we have in our problems 3 scenarios. Solve the deterministic model for scenario I, and then store this optimal solution for the first stage decision variables x. So what we basically do in this first step for scenario I, let's say that it's now 1, first scenario, we do what we did at the beginning of the exercise here. It will be here. These values will be x hat I. Then when we found this x hat I for every scenario j, so again, we now I is 1. Here it's 1. We found this x hat. And then for every scenario j, so again, for every scenario, we solve the deterministic model of scenario j with the first stage decision variables fixed to x hat I. So in this model, we will put this x. Instead of this x, we will put these values. Instead of demand, we will put demand for this I. So it's the first scenario. And then we will optimize it. And we will find the solution of this model. Then we will change j from 1 to 2. Again, we will put here the demand for the j for the second scenario, and again we'll optimize it. And then we will do it for the third scenario. And then since we know the probability, we can calculate the expected profit of x hat 1. Yes, and you see here it's just the expected profit. Now we are done with scenario I1. So with scenario 1, we can now change I to 2. We change I to 2, and again, we solve the deterministic model with the demand of the scenario 2, and we find the optimal third stage for this x hat 2. Then, in the deterministic model, we fix this solution x hat 2, and we solve the model with the data for every scenario. So with demand from every scenario, and we find this values of objective function, and again calculate the expected profit. And then we do the same when I is equal to 3, and again we calculate the expected profit. And then basically our solution of variables x, it's to find it, we check the best expected profit, which we calculated, and here it's 2100,2. And then we take as the first stage solution these decision variables, which are equal to x hat 2 in this case. So that this approach, it's more like an algorithm, but it also gives you the solution. So this was tutorial 3 and exercise sheet 3. We first of all we looked what is matrix notation for in linear optimization and constructed or identified these vectors and matrices for some small problem. Then we started the stochastic optimization, one of the main topics, and we constructed the optimization model for the Dakota problem, Dakota model. Then we added some stochastic elements to this model, and using this, due to the stochasticity, we created the expected value solution based on some model modifications. And when we have expected value, we could calculate the expected value of expected value solution. Then we use the second approach, which is this two-stage stochastic model to find the here and now solution. And based on that, we can evaluate the value of stochastic solution. And the last approach is to find the wait and see, which is more used for analysis. And when we have wait and see solution, we can calculate the expected value of perfect information. And the last, more algorithmical approach, it was the scenario analysis. And this bullet point E, you can use the information in the lectures and the solutions and like try to tackle it by yourself. If you have any questions, you can write in the forum or discuss on the questions and answers session. So have a nice day and goodbye, and thank you for the attention.